Think about the light from a regular lamp. It's a mess, right? It's a chaotic jumble of different colors spreading out in every direction. Now, picture a laser pointer. That's different. It's this impossibly straight, perfectly pure sphere of light. One is just chaos. The other is pure, engineered perfection. So how in the world do you take something as wild as light and force it to become so perfectly disciplined?
Okay, let's really look at the difference here. On one side, you've got the light bulb. It's throwing out tons of different colors, or wavelengths. Its waves are what we call incoherent. They're all jumbled up, totally out of sync. And the light just spreads out everywhere, getting weak really fast. A laser, though, it's the total opposite. It's monochromatic, one single pure color. It's coherent, meaning all its light waves are marching in perfect lockstep. And it's directional, a tight, powerful beam that seems to go on forever.
So that brings us right back to the central mystery. How do you actually tame light? How do you tell every single photon, every particle of light, to move in the exact same direction, with the exact same energy, and in perfect rhythm? Well, the answer, as it turns out, is hiding down at the quantum level. To really get what a laser is, you've got to understand the three fundamental ways that a photon of light can interact with an atom. This right here is the secret ingredient to the whole thing. First up is absorption. This one's pretty easy to wrap your head around. You've got an atom just kind of chilling in its normal low-energy state. A photon comes along with just the right amount of energy, and bam, the atom swallows it. It uses that energy to jump up to a higher excited energy level. That's it. Simple enough? Now, being excited isn't a stable way for an atom to live. So after a tiny, tiny fraction of a second, we're talking like 10 nanoseconds, the atom will just randomly spit out a new photon to get rid of that extra energy and fall back down to its comfortable ground state. This is called spontaneous emission. And because it's totally random, random time, random direction, this is exactly what's happening inside a light bulb. It's what creates all that messy, chaotic light. And here it is. This is the magic trick, stimulated emission. What happens if a photon flies by an atom that's already in that excited state? Well, instead of getting absorbed, the incoming photon nudges or stimulates the atom to release its photon right then and there. And here's the absolutely crucial part. The new photon that gets released is a perfect, identical clone of the one that nudged it. Same color, same direction, same phase. You started with one photon, and now you have two perfect copies. This is light amplification. This is the laser principle. But, just knowing the secret ingredient isn't enough. In nature, spontaneous emission, the messy kind, is happening all the time. But stimulated emission, it's incredibly rare. So to build a laser, you have to create a set of conditions that are frankly completely unnatural. You have to follow a very specific recipe. So let's just ask the question. If you look at any random group of atoms at room temperature, what are the actual odds that one of them is already in that excited state, just waiting for a photon to come along and stimulate it? The odds are this: 1 in 10 to the 30th power. That's a 1 with 30 zeros after it. I mean, it's a number so ridiculously small it's hard to even process. It means that in the natural universe, the conditions you need for a laser, they basically don't exist. And this right here is the whole point. A laser is a profound triumph of engineering. It's a machine that forces matter to do something that it would almost never, ever do on its own. We can't find a laser in nature. We have to build it. We have to cheat the system. So how do we cheat? Well, there are 3 rules. First, we need something called a population inversion. We have to artificially force way more atoms into the excited state than the ground state, the complete opposite of how things are normally. Second, we need to use a material that has a special metastable state. This is an excited level where atoms will hang out for way longer, milliseconds instead of nanoseconds, giving that stimulated emission a much better chance to happen. And third, we need pumping, a constant fire hose of energy, like electricity or another light source, to keep forcing atoms into that inverted state. Okay, so that's the theory. Let's see how these rules come together to build a real machine. One that many of us have actually seen in a science lab, the classic red helium neon laser. Every one of our rules is put into practice here. The mix of helium and neon gas, that's our active medium with that special metastable state. The pumping source is a high-voltage electrical discharge zapping through the gas. And then there's one other really clever component, the optical resonator. It's just 2 mirrors, one at each end of the tube. One mirror reflects everything, and the other lets just a tiny bit of light out. This setup traps the photons, bouncing them back and forth through the gas millions of times, stimulating more and more and more emission. It builds this incredible avalanche of identical photons before they finally escape as that perfect laser beam. So, let's follow the chain reaction. First, electricity pumps the helium atoms up to their excited state. Then, these energized helium atoms physically collide with the neon atoms, transferring their energy in a perfect exchange. This is how we get our population inversion in the neon. And finally, the neon atoms laze. They drop down in energy, releasing those perfect identical red photons. Those photons start bouncing between the mirrors, building up power until they burst out of the end as that iconic beam we all recognize. So, we did it. We engineered this impossible light. Now what do we do with it? Well, as it turns out, the answer is almost everything. Having the ability to create a perfectly straight, incredibly high-energy beam of light has totally transformed our world. We use it in factories for cutting and welding steel with unbelievable precision. In medicine, it's the invisible knife that reshapes your cornea in LASIK surgery. And hey, every single time you use the internet, you're relying on laser light, carrying data through fiber optic cables at the speed of light. It's the technology behind everything from 3D mapping of our entire planet to making holograms. You know what's funny? One of the inventors of the laser, a guy named Charles Townes, famously said that it was a solution seeking a problem. Think about that. The technology was so new, so revolutionary, that even the people who built it couldn't fully imagine all the incredible ways we'd end up using it. And that really leaves us with an amazing thought, doesn't it? The laser exists only because we figured out the specific rules to override nature's tendency for chaos and impose our own perfect order on light. It just makes you wonder, what other impossible technologies are out there just sitting in the quantum world, waiting for us to discover the right set of rules to engineer them into existence? You know, think about the light from a regular lamp. It's